Hi, everybody. Good afternoon. Well, good afternoon for me. Where I am, it's afternoon. Thank you so much for joining us. We're going to get started right away. I have a lot of data to share with you, and I want to make sure we get a chance to go through it. We had a slight technical difficulties, but I think we're going to be okay. I'm going to go ahead and share my screen, and we'll go ahead and start the presentation. A couple housekeeping remarks before we get started. When this is all over, I currently don't have the ability to look at chat or question and answer. But when we're finished and there's time for questions, I'll be looking at the question and answer box. If you have questions, please put them in the Q&A box in the Zoom. Feel free to chat during the presentation, but I won't be able to see those. So I thank you all for joining us today, and I'm excited to tell you about some of the work that we've been doing over the last, well, almost 8 or 9 years now at the Rodale Institute and at the Farming Systems Trial. I'd especially like to thank some of the funders. The Grantham Foundation and Organic Valley were really supplied the resources to be able to do the nutritional quality testing, and the William Penn Foundation has, through their through their support, we've been able to do a lot of the soil health testing in the Farming Systems Trial the last several years. There are 3 major research priority areas at the Rodale Institute are to support farmers, to adapt to and mitigate the climate change, and relevant to our topic today, human health and nutrition. And specifically under that priority area, we're looking at methods to solve food insecurity. We are an institution that has been heavily focused on crop production and soil health. So we're looking at ways that we can improve the nutritional density of crops and the foods that we eat. And we're very interested in investigating the links between soil health and human health. And some of the reasons we think this is so important is, if we define food insecurity as the chronic or episodic limited access to safe, nutrient-dense foods to support health, and if we look at developing countries like the United States, we can see that in most cases we're overweight. We have a high proportion of people that are either overweight or obese. In different reports, you can find anywhere between 70 to 78% of the U.S. population falls within classification of being overweight or obese. And in addition to that, the majority of the U.S. population is limited in key nutrients. So here in this graph, we're just showing those that are the most limiting: vitamin A, vitamin C, vitamin D, vitamin E, calcium, and magnesium. You can see vitamin D and vitamin E, over 90% of the population, over even those that are a healthy weight, are deficient in those nutrients. And in the other ones that we're showing here, more than 50%, and in many cases more than 50% of the population are deficient in those nutrients. And I don't want to dwell on it here, but we've seen that it's led, this has led to an increase in chronic diseases, despite the fact that we have access to food. But is this food safe, and is it nutrient dense, is the question that we're asking. And these issues are even more pronounced in the developing country, where there's more nutrient deficiency, and they can lead to even more severe diseases. And around the turn of this century, the early, around 2000 or so, was an area or a time when we really got alarmed. There was several databases that were coming out year after year that were highlighting a nutritional decline in our food. For the most part, they were highlighting a mineral decline in the foods. And you can see that these are coming from large-scale databases from the UK or the US over periods of time, sometimes 30, 40, 50 years, sometimes even longer than that. And it really got us at Rodale Institute thinking about being more serious about this motto that healthy soil equals healthy food equals healthy people, which is what our founder J.I. Rodale said when he started the Rodale Institute. And we spent a lot of our time focused on how to improve healthy soil, how to produce food without chemicals, how to produce food that is resilient to pests and insects. But we recognize that there's something happening in the world, and it looks like it was related to nutritional decline in the food. And we wanted to start to see, was there any link there between the degradation of the soil due to our farming practices or other aspects of farm production, and what role they're playing on human health. So we started the vegetable systems trial, and we have some other initiatives with healthcare organizations and hospitals, and started reaching out to scientists in the medical fields to start to understand this link between soil health and human health. And we realized when we were starting that we have a treasure trove here with our farming systems trial that was started in 1981. So we're, I believe, if I do the math right and count on my fingers, we're in the 42nd year of the farming systems trial that was started in 1981, as I said. And this is a 72 plot randomized replicated trial that has 3 different systems. It has an organic manure system that represents a typical livestock operation that has a longer crop rotation, perennial crops, hay in this case, and the access to dairy manure or beef manure that's composted and can put back onto the land. The organic legume system is a low input system that has had no external inputs during its history, and all the fertility comes from leguminous plant material. And then we have a conventional system which follows the standard practices that are in place in over 70% of the land in the United States today. And all of the recommendations for this system, in our case, because we're sitting in Pennsylvania, comes from Penn State and the Penn State Extension Service. So whatever they're recommending for farmers, to farmers for weed management and pest management is what we put into place into that system. In 2008, partly due to the technology that now existed, or at that time existed, for no-till in the conventional, as well as some pioneering technology that we and research at the Rodale Institute, we started to feel confident that we could include no-till into the system. So in 2008, we suddenly had 6 systems. The 3 systems that the organic manure, legume, and conventional, and then each of those were split into a tilled and a no-till system. The conventional system is a continuous no-till, so it has not been tilled at all since 2008. And the organic no-till is what we call a rotational till, because we're still tilling to plant our cover crops. So it's not complete no-till. And we now have 3 data sets that we were able to look at to start to make sense or start to understand this relationship between soil health and plant nutrient density. In 2014, every single plot in the entire farming systems trial was planted to oats. That was because we wanted to reset the crop rotations. So it was easy to plant oats in the spring and then plant different cover crops to prepare in the fall to prepare for new crops the following spring in 2015. Because each of the systems has different crop rotations, we don't have every single crop in every single system every year. So in 2019, wheat, there was a representative wheat sample in every system. And in 2020, corn was represented in every system. So we were using that as an opportunity to start to take a look and test some of these hypotheses around soil health and crop nutrient density. I'm going to just briefly touch on soil health because the data that I would show is going to be very much the same or consistent depending on what year we took it or what soil health indicators we took. They pretty much tell the same story. And here's a paper that was recently published by colleagues of ours and Emmanuel Mondi, who was the previous director of the farming systems trial, looking at some soil health indicators. And in this panel of graphs, the dark bars to the left are the conventional. The gray bars in the middle are the organic legume, and the far right panel or columns is always the organic manure. And this comes from soil taken at 3 different depths: 0 to 10, 10 to 20, and 20 to 30. We've been starting to recognize, we take deep soil cores to 1 meter in the farming systems trial every year, and we started to recognize that as we go deeper into the soil, some of these soil health indicators become even more pronounced or more improved in the organic system. So a couple of highlights here what we can clearly see from all of these is that there seems to be, or there doesn't seem to be, there is higher carbon levels, different types of carbon in the organic systems, and this is even higher or more pronounced in the organic manure system. So we have soil organic carbon, active carbon, which is a measurement of the more readily available, or carbon that can break down. It's more available to microbes, and it's also able to break apart and feed the crop, so to speak, by releasing or recycling and releasing nutrients. Microbial biomass carbon, this is the portion of the carbon in the soil that's made up of microbes, and then water extractable organic carbon. And in this study, they also measured soil structure, or measured wet aggregate stability. This is the ability for soil to hold together, as well as to form larger aggregates or larger clusters, which is relevant to the carbon story, because it looks like certain size clusters have greater ability to hold on to carbon, and that might be part of the reason why we see higher levels of carbon in the organic, and especially in the organic manure system. But similar to the carbon measurements, we can see that as we go deeper in the soil, this difference between systems becomes more pronounced. And the takeaway for this is that we see greater soil health in the organic systems. And when we look just within the organic systems, the manure system is the healthiest system. So that gives us a prediction or a hypothesis that if the healthiest soil is in the manure system, then we would expect to see greater levels of nutrients in our data sets that we're looking at in grain in the manure system. So here is soil data from 2014. And what I want to highlight here is that we clearly see in the minerals that we've tested in the soil, calcium, magnesium, phosphorus, and sulfur, that they are tending to be higher in the organic systems, and especially in the organic manure system. Anywhere we have letters next to a column or a data point throughout the presentation indicates that different letters mean that they're significantly different. So statistically significantly different from another treatment with a different letter. And that's usually to a p-value of 0.05. We can see here that the phosphorus is trending to be higher in the organic manure system. And then if we take a look at the same minerals in the oats themselves, we see what looks like an almost opposite trend. All of these that I'm showing here are significantly different between treatments in the oat grains, but they are tending to be lower in the manure system, not higher in the manure system, even though these minerals were higher in the soil. The answer might to some extent lie in the yield. And you can see that the manure system had the highest yields compared to the legume and the conventional system. And one important distinction here is that in this year, oats were planted without any additional fertilizer. We usually don't plant oats in the conventional system. That's not part of the crop rotation. But we also, in the conventional system, are usually putting down additional fertilizer, as you'll see throughout the presentation. So that could be relevant because the literature suggests that one of the reasons we've seen this negative yield or nutrient relationship, which we call the dilution effect, is that as we've bred crops to be higher yielding, or as we've applied fertilizers so that crops yield higher, we actually dilute those minerals throughout the crop. And most likely what was happening in the oats is that the manure system had higher minerals as well as carbon and nitrogen levels, which resulted in higher yields because the plant needs all of these minerals for optimal growth. But it also resulted in reductions in the mineral content of the grain. I did not statistically analyze this data, but using this as a graphical representation of an apparent dilution effect in the oat system. If we look at soil nitrogen and protein, which is related, since protein is made up of amino acids that have nitrogen as a compound, there should be a relationship. And there tends to be, I'd say with this graph, what we're seeing is probably an interplay between both a dilution effect as well as an increase in nitrogen, soil nitrogen in the organic systems. The protein levels were highest in the legume system, even though the manure system had higher nitrogen levels. It's possible that the yields were higher in the organic manure system, and that's why we're not seeing higher protein yields despite having high soil nitrogen levels. And the protein levels in the conventional no-till were the lowest of all the systems. So now I'm going to switch gears to our wheat data. Again, I'm starting off with soil chemical indicators taken in 2019. And again, we see that the majority of the samples that I'm showing are higher in the manure system. So the pH is optimal. It's an optimal pH in the manure and conventional system. The legume system is a little bit low. We see higher levels of total carbon and organic matter, which we've shown earlier in the soil health graph. We see higher levels of total nitrogen in the manure system than the conventional, but not between the legume and the conventional. And then higher levels of phosphorus, calcium, I apologize, it looks like that B under the manure should actually be A, so that there's higher levels of calcium in the manure system, as well as higher levels of magnesium in the manure system and sulfur in both of the organic systems compared to the conventional system. So again, we see greater levels of minerals in the soil in the farming systems trial. And this is not, we expected if we were to take samples every year, we'd probably continue to see these same trends. The soil health and soil indicators don't change so much that these will differ over just a couple of years. But again, this is over 40 years that is led to these changes. And now we're looking at the nutritional content of the wheat itself, the wheat grain. And we don't tend to see those same differences that we see in the soil. So it does look like iron is close to being higher in the organic manure system. It's right on the edge there of being statistically significant at the 0.05 alpha level. But magnesium was higher in the oat grain. And the other thing we see, though, is that when we look at protein and nitrogen-related nutrition like vitamin B6, and vitamin B6 is a mineral that, or I'm sorry, it's a vitamin that has nitrogen as part of its chemical component. So we see higher vitamin B6 and protein levels in the conventional, despite having higher nitrogen levels in the soil, which differed from our wheat results. But what could have caused that difference is that our standard practice in wheat management is to provide or to top dress the wheat in the spring with 60 pounds per acre of ammonium nitrate. And I don't show it here, but in addition to vitamin B6 and protein being higher in the conventional system, the majority of the amino acids were also higher in the conventional system, which makes sense because the data point I'm showing here is protein is a sum of all of the amino acids together. We also see, though, that the calories of the wheat are higher, and so that was an interesting result to us, and starts to get into this question of nutrient density, which I'll address in a few minutes. But we also recognize that we weren't seeing necessarily a strong relationship between soil nitrogen and protein in the crop. So we wanted to do a little, I'm sorry, let me back up. We wanted to investigate soil nitrogen levels in the crop because our previous data that I was showing you were from soil taken in the spring before the crop season, and doesn't necessarily tell us what the soil nitrogen levels are at the time that the crop is being formed and that during grain formation. So maybe we know that nitrogen is highly mobile in soils. It's prone to leach. It's prone to volatilize and be lost. So just because we measured it in the spring doesn't mean that it's there when the crop needs it. So in 2019 in the wheat, we took soil samples at 3 different dates after the conventional wheat was top dressed with nitrogen. So May 21st, June 4th, which that coincides with the beginning of head formation, and then July 3rd, which coincides just before harvest time. And what we found as we look at total protein and its relationship with total soil nitrogen, here I'm showing the soil nitrogen levels on June 4th. We see absolutely no relationship between soil nitrogen, protein, and I also did this for vitamin B6, although I'm not showing it here on the graph. So we're not seeing a very strong relationship between soil nitrogen availability and total protein. So that's the soil, but what about in the plant? Like I said, we want to measure not whether the plant is taking up the nitrogen and accumulating nitrogen and has that nitrogen available for protein formation. So in 2019, we also took plant tissue tests. We took plant tissue tests right at heading, so right when grain formation is beginning. So that's around the 10.1 or 10.5 stage. Very often the plants, because it's starting to be warm at this time, can go from 10.1 to 10.5 just overnight. So we took our measurements when the majority of the plants were in the 10.5 stage. And when we looked at leaf tissue nitrogen and total protein and vitamin B6, we actually do see a positive relationship. We don't show it here, but leaf tissue nitrogen levels were higher in the conventional system. We assume that is because of the additional nitrogen that was added. And we see a positive relationship between leaf tissue nitrogen, protein, and vitamin B6. There were no yield differences in the wheat, and so there does not appear to be any dilution effect. And so what this tells us is that there was sufficient nitrogen in the soil, in the organic systems, to produce an adequate yield. But the additional nitrogen and the nitrogen that was available to the plant resulted in increased protein. And this makes sense. We see this and we know that that's a strategy that some farmers are employing in order to increase protein levels and potentially get higher prices in the marketplace by having premium crop with higher protein, although that comes with high concern, especially for water quality and greenhouse gas emissions, because as we add more nitrogen in the form of ammonium nitrate or urea, or most ways that we're applying nitrogen in conventional systems, they're highly prone to leaching and being lost as greenhouse gas emissions. Where the sources of nitrogen in the organic system, things like cover crops and compost, break down slowly over time, and the nitrogen and other nutrients or minerals are available to the plant. So they're less prone to leaching or being lost into the environment. So the title of this talk was Nutrient Density in Grains in the Farming Systems Trial. So we wanted to start thinking about what is nutrient density, how do we measure nutrient density, and essentially what we're calling nutritional concentration, which is mostly what I've showed now, is you send a sample off to the lab and they tell you what the concentration of that sample is. Usually it's in grams per 100 grams or something along those lines. But it doesn't necessarily tell us whether or not it's more nutrient dense. And we also, a lot of times we're looking at one single nutrient, but there's multiple nutrients that make up the crop for us to be able to say whether this is a healthier crop than another one. And so we were searching for methods, and there's several methods that can be used. I'm showing here the nutritional quality index, but for the most part, we're taking the nutrient intake, or our sample, divided by the amount of energy, because we know that people can only eat so much. The typical or standard American eats about 200 kilocalories per day. But we also want to look at nutrients that are important for sustaining life and sustaining a thriving life. So really nutrients that are important for human health. If we have nutrients that we test for that aren't really deficient in the average diet, then they're probably not really contributing substantially to improved or degraded health. So let me run through some of the stats as we converted the wheat from a concentration of nutrients to a density of nutrients. And so here in the wheat, we're looking at the nutrient quality index score for calcium, iron, potassium, magnesium, zinc, vitamin B6, and protein. These are the minerals that are most deficient in not just the American diet, but also globally. If we had more data, we could add more vitamins. Vitamin B6 or B vitamins tend to be higher in wheat than some of the other vitamins, but we could also be looking at things like fiber and potentially gluten to add more data points to this. And then we look at the sum of all of those nutrients or of all those scores to be able to come up with a total nutrient quality score, and then be able to compare between systems and start to say, was this grain produced under this method healthier or less healthy than another one? To date, this is mostly being used to compare different crops, maybe lettuce and spinach, or potatoes and beets, or even it's being used to look at different products in the marketplace, maybe soup that comes from two different companies, to determine whether or not one is healthier than another. To our knowledge, it hasn't necessarily been employed to compare nutritional density of food that has been grown under different conditions. So we think this is novel and in a way that we should be going. If I look at the data here before me now, as I look at this data, it's suggesting that we can't clearly say that the manure system or the organic systems are more nutritious than the conventional system. So now I'm going to move to the corn database from 2020. I'm not showing any soil mineral data here. Like as I said, It's not going to be very different from the data that I showed previously. So I've jumped right to the corn grain data. And here we're actually seeing a reverse or different than, well, I guess it's not soil data, but we're seeing calcium and zinc are higher in the conventional corn. And we're not quite sure why we would have seen that. We would maybe have expected, again, we didn't have a yield difference, so we didn't necessarily expect that the dilution effect would be an issue. But one thing to point out in this is that in the corn system, the varieties between the conventional and organic systems are different, because in the conventional system, we're using genetically modified crops, or GMOs, that are tolerant to herbicides as well as tolerant to caterpillar pests. And the corn in the legume and the manure system is certified organic. GMOs are not allowed in the organic system. So they're completely different varieties. I say that because there's potential that the differences that we're seeing here are due to varieties and not necessarily due to soil health, levels of minerals in the soil, or things like yield that could impact mineral levels. But we also wanted to look at the nitrogen nutrients, so the B vitamins again. We expanded our list of B vitamins, as well as included total protein here. And what we found is that the organic systems, and again, especially the manure system, had higher levels of B3, B6, or niacin, which is B3, B6, folate, and total proteins. But in this case, there was no difference between the total calories of the crops. For the most part, it's probably worth pointing out, I'm showing the systems without the till versus no till. And the reason for that is we see almost no differences in not only soil health, but also especially the crop nutritional measurements between the tillage systems. They almost all, the differences we see are between these systems, which suggests that it's not tillage, but it's the overall management of fertility and pest management that are playing a greater role in regulating nutrients. In the corn, similar to the wheat, the conventional system receives additional fertilizer. So we apply 160 pounds of ammonium nitrate to corn every year in the conventional system. 100 pounds of that goes down at planting, and 60 pounds comes later in the season, side dressed. And so the reason for that we don't put it all down at one time is because it's prone to being lost through leaching in the environment, especially during heavy rains in the spring. So we're trying to be responsible farmers. But it's also worth noting that we recognize as agronomists that corn has a high nitrogen need. And so in the organic systems, we are still tailoring our system so that we will provide adequate nitrogen for the corn. So for the most part, that's being accomplished through planting a hairy vetch cover crop in the fall that is then either rolled down and planted directly into in the organic no-till system, or it's plowed and turned into the soil where it can break down and release nitrogen in the tilled systems. And again, the organic manure system receives additional nitrogen in the source of composted dairy manure, but that's actually more recently been applied after oats, not before the corn. So some of that nitrogen is probably still from the compost is still available to the corn, but a lot of it has been used by the two previous crops. But anyway, it made us think it looks like there's additional nitrogen in the organic systems that's leading to increased protein and vitamin B levels. So now switching over to the nutrient quality index score, the trends of each individual nutrient were very much the same. because we saw significant differences and because the calories were not different. So we didn't expect to see a drastic change in this calculation since calories didn't differ. But overall, again, similar to the wheat, there was no significant difference between the sum or the total nutrient quality index score. So again, we can't say completely that there's a difference in the nutritional quality of the corn grown in one system over another. And we had data that the Soil Health Institute had collected on using the Cornell assessment of soil health. And I quickly did an analysis of that to see if there was any relationship between the NQI, or the sum of the net nutrient quality index score, and the Cornell soil health rating, and I found no relationship. So unfortunately, we're not showing a real strong relationship between soil health and human health, at least in the nutrients that we're measuring. Like the wheat, we wanted to get a better measurement of the nitrogen that was accumulated in the plant, not just in the soil. So for corn, we took plant tissue test measurements, or plant tests at 2 different times of the year. We took a plant tissue test right at silking. So that's the R1 time. And silking is when the corn begins to pollinate. So it's just before grain fill and the formation of the grain. And then we also took nitrogen levels using the late season corn stalk nitrate test, which is done usually just after physiological maturity, but not too far after, where the plant has completely dried down. So there's still adequate amounts of nitrogen in the plant that haven't been translocated. And when we look at those, we actually see much higher levels of nitrogen in the organic plants than the conventional, which explains why there would be higher levels of nitrogen-related nutrition in the organic systems. And while I don't show it, you can see that their tillage did have an impact. And so in the organic systems, tillage actually increased the plant tissue and late season corn stalk nitrate test. So most likely that tillage, not only did it put more of the leguminous cover crop into the soil so that it can break down and release nitrogen to be available to the plant, it also increases respiration, which creates mineralization and again releases more nitrogen. What I suspect in the conventional system is because the nitrogen, nitrogen levels inherently in the soil, or not inherently, but that are present in the soil naturally. I'm saying that wrong. They're present in the soil not naturally, because of our management, are lower, and potentially the loss of nitrogen through leaching or through off-gassing resulted in low plant tissue nitrogen levels in the conventional system. And again, we used that data to take a look at the relationship between plant tissue nitrogen. In this case, this is the plant tissue test, not the late season corn nitrate test. And we see both protein and vitamin B6 are positively correlated with the percentage of plant tissue nitrogen in the plant. And we did statistically analyze this, so we can say there is a positive relationship statistically. Similar to the wheat, we saw no association between yield, protein, vitamins, or minerals. I should also point out that, similar to the wheat, that while total protein was higher in the organic system, the majority of the amino acids that we tested were also higher in the organic system, again, because the total protein is a sum of all of the amino acids. And one thing for us to look at in the future is the protein quality, or the relative abundance of the essential amino acids compared to the total amount of protein. But again, there doesn't seem to be an apparent dilution effect. And we actually see, interestingly, that the conventional till is actually the lowest, well, I guess the legume till, but is one of the lowest yielding systems. And so some of the conclusions based on this data are that the soil mineral depletion hypothesis is not supported. So early on when I said that there was databases that were analyzed and showed the nutritional decline in many of our crops, one of the first things we thought about was, well, it's because of the decline of those minerals in the soil. And that's what's resulting in depletion of mineral in our grains and in our crops that were being assessed in those databases. But from looking at just a couple reference points here, we think there's something else that's going on that's important to highlight. So here is data from wheat that's grown in the long-term broad bulk wheat trial at Rothamsted. This started in 1843. So they have data from wheat going back from 1843 till today. This was published in 2008. And what you see is that from 1843 to about 1960, you see very little change in total yield. You see very little change in the harvest index. And the harvest index is the grain divided by the total plant biomass. But in 1960, you start to see this increase in grain yield, increase in the harvest index, which is what you might expect to see, because breeders are looking at the harvest index to try to make a plant or create a plant that is more efficient by utilizing photosynthesis and putting more of its energy into grain production and less of it into stalk and root production. So for that reason, you tend to see increases in a harvest index. And also around that same time, we start to see wide-scale adoption of these semi-dwarf wheat varieties. So we've gone from a traditional wheat variety that's taller to a semi-dwarf wheat variety because they produce more yield. And 1960 was when they started to adopt those semi-dwarf wheat varieties in the broad bulk wheat trial. And so we start to see a decline in zinc, this decline in iron, decline in copper, decline in magnesium, these important minerals. And so this study is basically showing us that most likely it's not a depletion in the minerals in the soil, because there didn't seem to be much change for over 100 years. And this study is also looking at different fertilizer management strategies. And then here's another study that looked at corn. This isn't corn that was, excuse me. The graphs that I'm showing here are not changes in the corn that was grown between 1920 and 2000. This is the differences in corn that was released or bred and came onto market between 1920 and 2000. And then they were grown side by side at 3 separate locations using the same fertility methods. And so we can see that those varieties that have came out increased in starch and had a decline in protein. And this is consistent with the databases that we were looking at, a consistent decline in minerals, decline in protein, and increase in carbohydrates and starch. Again, still a very high concern to human health that this is occurring, but it's not pointing toward depletion of soil minerals, but more toward breeding and variety selection as a reason for that decline. So as we look at research horizons, we're going to continue nutrient density testing. We have a recently funded study from the Foundation for Food and Agriculture Research with the partners that you see here. So it's a collaborative project that's going to be looking at wheat at long-term systems trials that are comparing organic and conventional systems across the country, as well as some controlled studies that control more for nitrogen. We can control more for variety, which was an issue in some of the studies that I just sent. We're going to be doing in-depth in-depth microbial analysis to start to understand the association between microbes in the soil and the nutrients in the plant. We also want to recognize the Bionutrient Institute and the Real Food Campaign. So we'll be contributing samples from the Farming Systems Trial and our Vegetable Systems Trial to the Real Food Campaign, which is developing or has already developed, but it's adding to a large-scale database that matches nutrients, including phytochemicals like polyphenols, and soil properties and farming practices. And there's several other databases similar to this that are starting. So we're really starting to see the world waking up to the fact that we're in poor health, and our food system is really plays a major reason why. And you can't separate food system from food production or farming, and you can't separate soil from farming. I also see that a real need for ecological breeding, of breeding programs and selection of crops that are focused on improving nutrient density, that are focused on functioning well in organic and regenerative organic and low input systems. The majority of our breeding over, as I mentioned in those last couple slides, has been highly focused on yield and also focused on responding to chemical inputs, especially fertilizers. So we don't necessarily have crops that are adapted to organic and regenerative organic systems if we make a mass shift like we think is going to happen and think it needs to happen in our society. And we need to develop comprehensive farming and food systems models. They need to be local and integrative. At the Rodale Institute, we've started to, we put a farm at a hospital, and we've started to engage hospital and healthcare organizations so that we can create methods to grow farmers or to train farmers so that we can grow the number of farmers, as we know that we're going to need more farmers to produce food, but at the same time get that food into areas where there's low income and low access, which we, from a research perspective, then want to look at those models, see if they're profitable, and see the impact they have on human health, on the populations that are now having access to healthy organic food. And this gets us to the point that we really just need to eat better. If you look on the graph on the left, this is if you're left of 0, this is the proportion of the US population that gets below the recommended amounts of the vegetables, fruit, dairy, grains, or protein. And above 0 is the proportion that get above or get the adequate amount of each one of those food groups. And since we're talking about grains, if you look just at US grain consumption, this was 2005 recommendations, you see that we eat about the right amount of grains. 100% would indicate that we eat, the right amount of grains in our diet. But only 34% of the people are getting their calories from whole grains, which are nutrient dense, and the majority of people are getting their grains from refined grains that are not nutrient dense. So there needs to be societal shifts in how we eat, but to the point that I was making before about models, we need to change and transform the ways that we're producing food and getting food to people and to the right people that need it. And lastly, we think the power of biology is a new area of exploration. It's already begun. We have been taking bacterial and fungal population measurements in the Farming Systems Trial recently. We're seeing clear differences between systems and also impacted by tillage. Fungi especially are highly impacted by tillage, while bacteria and fungi are both impacted by systems, which indicates that chemical inputs are shifting the soil microbiome in one direction, while organic inputs like cover crops and compost are shifting the microbiome in another direction. The question is it good? Is it bad? Can we indicate or start to understand the interplay between the soil microbiome and the gut microbiome that most likely is occurring as it goes through our food? And to finish up, I just want to acknowledge a few people, especially Dr. Chao Rui, who is the current director of the Farming Systems Trial, Annie Benson, who is the research technician who oversees the data collection of the Farming Systems Trial, and Dr. Emmanuel Monday, the previous director of the Farming Systems Trial. A lot of the work that I presented was collected during his tenure here at Rodale Institute. And I'm sure I'm missing names because just about all of our research technicians, all of the interns that we have here at Rodale Institute have helped take some data collection in the Farming Systems Trial, and as well as our farm director, Rick Carr, and Dan Kemper, who are responsible for the day-to-day farm operations and management of the Farming Systems Trial. So thank you for your time. I'm going to leave this slide up for 1 second. So if anybody needs to get down my email address with questions that I might not be able to answer in the next few minutes, feel free to do that. But I'm going to stop sharing my screen, and then I'm going to look at Q&A and answer some questions. Okay. So I don't know if you see me or see the screen, but it looks like. Okay, so I have a question here that says, commercial corn for export kernel changed more lignin, so less cornmeal when unload customer port. They ordered whole grain. How has organic changed or not versus commercial corn? I'm not sure if I completely understand the question, but I think I understand the end. How has organic corn changed versus commercial corn? I don't know if I have a really good answer to that. We have another database that we're looking at over, I think, about 13 years in the Farming Systems Trial that will look at, it's analyzing corn, soybean, oats, and wheat, and it has multiple years component. I might be able to answer that more in depth, but just I haven't dug into the literature enough to be able to answer the question of how organic corn might differ from commercial or conventional corn. I'm sorry, I can't answer that responsibly. And I don't see any other questions. I will say, not necessarily conventional or organic, but there are some interest in improving or increasing the nutritional density of corn and other grains, specifically things like methionine, other proteins, in soybean oleic acid. These are things that the market for corn, especially for feed, and soybean as well. But these are things that the market is saying we want. There's a benefit to the processors to have these varieties. So there does seem to be a little bit of push by the market for what might be called more nutrient dense or higher concentrations of certain nutrients. I don't see any other questions, so I thank you very much for your time and your attention, and I'm going to end the webinar there. Thank you, everybody.